Hello students, today under the topic matrices and determinants, we are going to learn about how to solve the system of simultaneous linear equations using matrix method. Now the matrix method is used when the coefficient matrix is your non-singular matrix. Non-singular matrix means whose determinant is not equal to 0. Now see, if we are given a set of linear equations, right, like x plus 2y equal to 4, 3x minus 5y equal to 1, then this system can be written in the form of matrix, like we can separate the coefficients of x and y, right? So the coefficients of x will make the first column of the matrix like 1 and 3, and the coefficients of y will make the second column like 2 and minus 5. Now the two variables are x and y, and it's a system of your two linear equations, so it will be a 2 cross 2 matrix where the two variables are x and y, right? So this represents your coefficient matrix, this represents your variable matrix, and is equal to, this is the constant matrix which is called as B. So this is the matrix form of system of linear equations. Under applications of matrices and determinants, we will discuss the application of determinants and matrices for solving the system of linear equations in 2 or 3 variables and for checking the consistency of system of linear equations. Now, we are already aware what are the consistent systems. A system of equations is said to be consistent if it has solution, like either it is one solution or more. If the solution of system exists, then we say that the system is consistent. Whereas inconsistent system is that in which the system of equations is having no solution. Okay, so a system of equations is said to be inconsistent if its solution does not exist. Now, the solution of system of linear equations using inverse of a matrix, right? So let us express the system of linear equations as matrix equations and solve them using inverse of coefficient matrix. Now see, consider the system of equations. Here we are considering three equations including three variables x, y and z. So a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, a3x plus b3y plus c3z equal to d3. Now this system is having A as the coefficient matrix. So see, we will be taking the first column as the coefficients of x like a1, a2, a3. See from here. The coefficients of y will make b1, b2, b3 second column, and coefficient of z will make the third column. X is the variable matrix, which is, we have three variables x, y and z, right? So for the product of this to give you this result, we should be having our matrix A as a 3 cross 3 matrix and matrix X as 3 cross 1 for the product to be possible. And the overall result should be a 3 cross 1 matrix, so that we can compute it to a 3 cross 1 coefficient matrix, which is d1, d2, d3. Now the system can be expressed as Ax is equal to B. A into x will give you this result is equal to B, right? Now the two cases arise. Case number one is, if A is non-singular matrix, then its inverse exists, right? And the second case is, if A is singular matrix, then determinant A is equal to 0. And in that case, we have to apply some other method. Now let us see first case. If A is non-singular matrix, the system can be written as Ax equal to B. Now pre-multiplying both sides by A inverse, we get A inverse into Ax is equal to A inverse into B. Now this A inverse A will follow the associative law, and A inverse A is equal to I. So it becomes Ix, and this is same as A inverse B. And Ix is equal to X is equal to A inverse B. So this matrix equation provides unique solution for the given system of equations as inverse of matrix is unique. And this method of solving the equations is known as matrix method. Means if the system is of the form Ax equal to B, then its solution X is equal to A inverse B is called as the matrix method, right? And we will get the values of the variables x, y and z. Whereas in case number 2, if the matrix is singular, that is determinant equal to 0, in this case we will calculate adjoint of A into B, right? So if adjoint A into B is not equal to 0, right, means it's not equal to null matrix, then the solution does not exist and the system of equation is called inconsistent. Whereas if adjoint A into B equal to 0, then system either can be consistent or inconsistent according to system have either infinitely many solutions or no solutions. So in this video, we will study our case number 1. So let us take the example concerned to it. Solve the system of linear equations, and the system of linear equation here is x minus y plus 2z equal to 7, 3x plus 4y minus 5z equal to minus 5, 2x minus y plus 3z equal to 12 using matrix method. So let us start solving it. So first of all, we need to write that the given system can be written as Ax is equal to B, right? So Ax equal to B means A is the coefficient matrix, so it is 1, 3, 2, first column. Second is minus 1, 4, minus 1. Third is 2, it is minus 5, 3. Into x, the three variables are x, y, z equal to B, the constant, right? So where my A is your coefficient matrix and x is the variable matrix and B as the constant matrix, right? So the very first thing I need to understand is, before applying this method, that I should check my determinant of A, because this method is applicable only when the matrix is non-singular, that is determinant is not equal to 0. So let us see, the determinant is 1, 3, 2, minus 1, 4, minus 1, 2, minus 5 and 3. So it becomes 12 minus 5 plus 1. I am expanding through row number 1. So it is 9 plus 10 plus 2 into, this is minus 3 and minus 8. So this becomes your 7 plus 19 and minus 22. And this result is 26 minus 22, that is 4, which is not equal to 0. So therefore, given system is consistent and having unique solution. Why? Because your determinant A is not equal to 0 and A is non-singular. So in case of non-singular matrix, we can apply our matrix method, right? So in this case, our system is of the form Ax equal to B. So solution is given by x is equal to A inverse B, where this A inverse can be calculated by using adjoint A divided by determinant A. We can divide by determinant A as it is not equal to 0. Whereas in case number 2, division by 0 is not possible, right? So that's why this matrix method is applicable when your determinant of this matrix is non-singular, okay? So which is not equal to 0 means matrix is non-singular. Now adjoint A is equal to the matrix obtained by replacing each element by the corresponding cofactor. So E11, the corresponding cofactor is C11. Similarly, C12, C13, 21, 22, 23, 31, 32 and 33, and then take its transpose. So my matrix A was 1, 3, 2, minus 1, 4, minus 1 and 2, minus 5, 3. So we know that Cij is minus 1 raised to power I plus j mij. Mij is the minor, and like for minor of 1 will be for a 3 cross 3 matrix, the minor will be of order 2 cross 2. So to get minor of each element, like for C11, what I need to do is delete this row, delete this column, and then compute the rest of the determinant. So similarly, let's start framing C11, C12, C13, right? So this sign will be negative as my power will be odd. So minus 1 will be raised to odd power, so result will be negative, rest of the 2 will be positive. So let us start framing. So for it is 1, it is 4 3s are 12, minus of, like minus 1 into minus 5 is plus 5, so it is 12 minus 5, that is 7. For C12, it is 3 3s are 9. So overall negative sign is there. So it is 3 3s are 9, and minus of 2 into minus 5 is minus 10. So 9 minus of minus 10 is plus 10. So this will be minus 19. For C13, it is, leave this 2, right, this row and this column. So it is minus 3, minus 8. So it is minus 11. Similarly, 2 1, 2 2, 2 3. So 2 1 will be for the 3 like this. So it is your minus 3 and plus 2. Minus 1 into 2 is plus 2, that is minus 1. For C22, like this 4 we are having. Okay, so overall result of this negative sign will also be there. We need to keep it in mind that my as the power is odd, so overall negative result will also be there. So this will be your minus of minus 1, that will be plus 1, right? So don't forget to it. So you can put a negative sign in advance to avoid this mistake, right? So for C22, it is for 4, like it is 3 and minus 4. So it is minus 1. For 2 3, it is like this. For minus 5, delete this row, delete this column. So it is minus 1. Minus 1 is outside, right? So this is for minus 1 and plus 2, which is your minus 1. Again for C31, C32 and C33. So my negative sign will be here. So C31 is here, my 5 minus 8, that is minus 3. For this minus 1, it is minus 5. Be careful about this negative sign outside, right? So this is your C32 is minus 5 and minus 6. So it is plus 11, right? And for the last one, 3, it is 4 plus 3, it is equal to 7. So let us obtain the adjoint matrix. Let us obtain the adjoint matrix by replacing each element with its corresponding cofactor. Minus 19 and 13. This is 1, minus 1, minus 1, minus 3, 11 and 7 and its corresponding transpose. So my adjoint matrix will now be, transpose will be interchange rows and columns. So this first row will become the first column, and this is 1, minus 1, minus 1, and it is minus 3, 11, 7. So this is your adjoint matrix. Now let us compute our A inverse, right? So what is, now A inverse is given by 1 upon determinant A into adjoint of A. So determinant A was 4, so it is 1 by 4, and the adjoint matrix that we obtained recently, 7 minus 19 minus 11, 1 minus 1 minus 1, and it is minus 3, 11 and 7, right? So the system was of form Ax is equal to B, whose solution is given by x is equal to A inverse B. So A inverse will get from here. So x is my variable matrix, and this is A inverse will get from here 1 by 4, 7 minus 19 minus 11, 1 minus 1 minus 1, minus 3, 11 and 7, and B is my constant matrix. So B is 7 minus 5 and 12, right? So to get the overall result, let us multiply. So this is row and this is column. So it is 49 minus 5 minus 36, right? It is minus 19 into 7 is minus 133 plus 5 plus 132. And it is minus 77 plus 5 and plus 84. So what do I get? So this is 1 by 4. 49 minus your 41 is 8. From here I'll get 4, and this will give me 89 minus 77, that is your 12. So let us divide by 4. It becomes 4 to the 8, 4 ones are 4, and 4 threes are 12. So my x, y, z matrix coefficient equated to the variables are x is equal to 2, y is equal to 1, and z is equal to 3. So to check whether this solution is correct or not, I can put this in any of the equations. Okay, so let us take any of the equations. So first one, I am taking x minus y plus 2z is equal to 7. So put the values to check whether my result is okay or not. So 2 minus 1 plus 6. So this is 8 minus 1, which is equal to 7, and which is equal to my right hand side. So this is the correct solution.